Welcome to the class, good sir.
Hello, thank you.
What are you busy with at the moment? Are you preparing for maths or something?
Yeah, math
So you haven't
at
done
this
any
moment.
physical science recently?
Yeah, I had to do life science, so it's hectic.
Okay. Just want to make sure that we all are on the same wicket. So thank you for moving the class or allowing the class to be moved. Do we have a... No, you don't have maths classes. You only have... So you have a class today and then what? Next week? Not? No. We know you're writing physical science.
Physical science, 2 weeks.
Oh,
Yeah, in 2
okay.
weeks.
Do we have
Next week,
class
I'm
next
like,
week?
sorry?
Do we have class next week?
Class next week.
No,
Yeah, I think
I don't
so.
know. I don't know. Why don't I have it booked for next week? It's normally on what? Thursdays at 10:30.
Yes, it's on Thursdays. Okay, I can see. It's because then I think it's because there's math on Friday.
Yes, that's why we're not having it, because we probably moved it out because you're not going to attend that class if you're writing maths the next day. Okay.
Yes.
So that class we don't have, and then you're writing on the 25th.
The
Paper 2.
21st, yeah, the 21st and the 25th.
Is that the first or the second paper?
First paper.
On the 25th.
Yeah, the first paper. On the 21st, the first paper.
I don't have that date. Oh, I've got that date. Okay, we'll start in a minute. We're just waiting for... Okay, let me make that one purple. What? Oh, okay. So I'm seeing you over the weekend then. Yeah. Okay, that's okay. Next week we don't have that Thursday class because we're doing it on Sunday.
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 Okay.
4:15 to 5:15. We can make it earlier if you want to. Maybe that's better because I'm late.
Yeah, that's fine.
Okay. So where is Bernice? Right, so we've got those dates. I'll remind you again of them.
Right.
What are we doing today?
Revision.
Really?
Past, yeah.
Which,
Needs revision.
have we finished with chemical equilibrium, the graphs?
No, we haven't.
Okay, so we'll go do that. We'll just work through a couple of them, and if there's time left, we can start with revision. Okay, let's start. It's 11 o'clock. As good as not here. Right, just make sure you've got a calculator and paper and everything.
All right.
Do you have it?
Yeah.
Okay, good. Okay, let's start. Chemical equilibrium. Okay, there's the example of the graphs. The graph below shows 3 different stresses on the reaction given. So this is the reaction here. And there's 3 different stresses at various times. So there's a stress 1, it's blue there, and stress 2 and stress 3. If the stress that changed, let's read 5.7. If the stress that changed at number 1 corresponds to when William cooled the reaction vessel, explain whether the forward reaction is exo or endothermic. So basically what they're saying, is that this vessel was cooled down, so the temperature was reduced. So at number 1, we lowered the temperature. No, yeah, we want to cool down, so we lower the temperature. They want you to explain if the forward reaction is endo or exothermic. Have a 5-second look at that. Do you want to copy the graphs, or are you happy just looking at the screen?
Now I'm fine with looking
Okay.
at the screen.
So what happened at interval 1? Well, this is a small mistake here. That must be NO2. So the nitrogen dioxide gas increased, the chlorine gas increased, and the NOCl decreased. So if I increase or decrease the temperature, then the NO2Cl gas decreases and other one to increases. So is the forward reaction, is that endo or exothermic? Okay.
Exo.
A decrease in temperature favors what? The exothermic reaction. So the forward reaction is exothermic. Very good. And my reason is explain whether the forward reaction is explain. So I can't just say forward reaction. I will say for 1 mark, the forward reaction is exothermic. And my explanation is as follows. A decrease in temperature favors the exothermic reaction because the amount of mole, or this is concentration basically, it's very small. I don't know if you can see that. That's written as mole per liter, which is the same as mole per cubic decimeter. So the concentration of the NO2 gas and chlorine gas increases, while the concentration of the NO2Cl gas decreases. That's 2 marks. So 1 mark for the answer, 1 mark saying the decrease in temperature favors the exothermic reaction. The forward reaction is exothermic because those 2 gases increase and the reactant decrease. Okay, explain fully the change that took place at the interval marked 2. This is a difficult one. This is an unfair one. So if you don't know, then you guess. And then you test the change that you actually made. By eliminating others. We can either change concentrations, we can change temperature, we can change pressure. If I increase the pressure, all 3 of those won't increase. No, it will increase. It will increase. The concentration of all 3 will increase. Why? If I increase the pressure, the only way to increase the pressure, or there's 2 ways of increasing the pressure. One of the ways of increasing the pressure is by reducing the volume of the flask. If I reduce the volume, concentration is the amount of moles divided by the volume. If I reduce the volume, the concentration of all 3 of something will increase anyway. So both concentrations has increased. You agree? All 3 concentrations increased. So I can answer that I've increased the pressure by reducing the volume. But let's just test if that's true. Because if I increase the pressure, the reaction that has the least amount of moles of gas will be favored. So the reverse reaction will be favored. Do you agree? So by increasing the pressure, the reverse reaction will be favored and the amount of NO2Cl must increase. And that is true. That increased, and these other 2, let's make them yellow, they will decrease. There's also another explanation. You could have increased the concentration of all 3. But I think that pressure is a better one. I'm just slightly worried about the fact that these are all exactly on the same level again. That can't be true if I increase do you agree? If I increase the concentration of all three, they can't go back to the same concentration level they were. They must be slightly higher, all three of them. Okay, so this is the correct answer. We increase the pressure by reducing the volume. And our explanation is as follows. So we increase the pressure by reducing the volume of the flask. Increase in pressure will favor the reaction site that produces the least amount of moles. The reverse reaction, or the very reverse reaction will be favored because NO2Cl has got the least amount of moles gas. And therefore that one will increase and decrease. Okay, good. That's easy. 5.9. Would the value of the equilibrium constant between intervals 1 and 2 be the same as between 2 and 3? So what they're saying is as follow. If you look at this part here in yellow, where equilibrium is, and the part that is in blue, that is also where equilibrium has been reached, will the Kc value of those two areas be the same? And explain. I know you haven't now studied these things, you were busy with other work. But see if you can answer that. Let me ask you the question in reverse. What changes the Kc value? Which one of those? How can I change the Kc value of any reaction that is in equilibrium? Do you know this, Kutsu?
Changes in Kc.
I can't hear you.
I think I do.
Yeah, take a guess. There's only one of those three changes that you can make that changes Kc value, and that's only the temperature change. A change in temperature is the only thing that changes the Kc value. And in this interval 2, we didn't change the temperature. So there's no change in the Kc value. And my explanation is as follows. There's no change in the Kc value, and the reason is we did not change the temperature at interval 2. The temperature is the only change that changes the Kc value, that allows for Kc values to change. Are you happy?
Yeah.
Good. Oh, damn. Let's get back. This is some acids and bases with pH in it. We're not going to do that now. Let's go to this graph. Right. 4 moles of gas X and 4 moles of gas Y is added to a 2 decimeter cube container at a certain temperature. The following equilibrium is established at a certain temperature. Temperature doesn't matter. What the temperature is not important. You don't work with it. You just need to know if it's forward or reverse, is indo or exothermic. How many moles of X2, Y3 are formed by the time reaction reaches equilibrium in 30 seconds? That is 1 mark. Is that difficult?
No, it's one.
No, it looks like 0.5.
Really?
Can you read from the graph?
Oh, okay. Yeah, no, I read that wrong. Okay.
You didn't look at the graph, you just guessed. Oh, you tried to work with the mole ratios, is it?
Yeah.
No, you
Yeah.
can't. Remember, when a reaction is in equilibrium, it's not a normal reaction. It's not X plus Y and then we produce XY. In other words, we used to think that now everything is finished. All the X is used up and all the Y is used up and now we've got XY. Or maybe the Y is not even used up, but one of them must be used up. It's not true. Remember, this is for forward and reverse reaction. So X forms the whole time and X reacts the whole time. So none of the stuff will ever be finished. They will always be there, all of them. So even if I put 10 moles of X in it, it doesn't mean I'm getting 5 moles of X. No, it doesn't. It depends on where the equilibrium is. Maybe I can get 5 moles if I increase the temperature or lower the pressure or whatever. But this system will just stay in equilibrium at any amount that it's comfortable at. Right, calculate the value of the equilibrium constant at T50. And this is 6 marks. So what does it tell me? In order to accomplish something like that, we need to do what? Remember, when you see that in an exam, then you exactly know there's only one way of doing it. And that is by drawing what? A table.
A table, oh yeah.
Yes. So when it's 5, 6, or 7 marks and it's got to do with Kc values, they want the Kc value or they give you the Kc value and they want some other concentration or something. Then you just draw a table that just gives you some, it just makes order to to the process of thinking. Gives you some order. So I've got X here and Y here and X2, Y3 in the ratio of 2 to 3 to 1. And this is that ice table. So that I is initial, and we are going to be working with mole. And C for change, mole. And E for equilibrium, again in mole. And because we're using a mole table, then I have to also get equilibrium, the concentration there. So mole per decimeter cubed. So let's read. Right at the beginning, we are adding 4 moles of this gas, 4 moles of that gas to a container, and there's 0 of that. Now at 50 seconds is here somewhere. We have equilibrium, and the amount of mole of gas X looks like 3. And the amount of mole of X2Y3 that formed is 0.5. So I added, or it increased by 0.5. This decreased by 1 mole. And the Y will always be 3 times more than the X2Y. So this one decreased by 3 mole. You happy with that?
Yeah.
No, that was wrong. Can't be happy about that. 0.5 times 3 is not 3. It's minus 1.5. So this ratio must also be 2 to 3 to 1. Whoa. Let me just take those numbers out because they can be confusing. So at equilibrium, I have 4 minus 1.5, which is 2.5.
Okay.
And then I can work out each concentration. The concentration is the mole divided by the volume. So the concentration here is 3 divided by 2, and that's 1.5.
Why is it 2.5? Why is it 2.5?
Where? Oh, I didn't change that yet. I didn't change that yet. Oh, no. Which, this one, yeah.
Yeah.
What is 4 minus 1.5?
Oh, I said 0. Okay, never mind.
Good.
Yeah, it's 2.5. Okay, never mind.
2.5 over 2. What's that? It's 1.25, isn't it?
Yes.
And the last one, I have a concentration of 0.5 divided by 2, so that's 0.25. So now we've done this. We've used our table, and the only thing I need to do is write down a Kc expression, which is y2 x3 divided by x to the power of 2. Okay, let me just redo that too. Can you see where I'm writing now at the moment?
Yes, I can.
The edge of my screen, and y to the power of 3. So our Kc expression, if you put those values in, I have 0.25 divided by 1.5 squared times 1.25 to the power of 3. Let's put that in a calculator. 0,07. No, 0,057. It's very low. 0,057. And there's no unit for Kc value. For Kc values. Right? You can screenshot it if you want to. You can always go back to the video online if you don't want to save it or write it down. I know you're not focused on this now, but it's fine. There's a couple examples more. Right. The reaction represents the following balanced chemical equation. Blah, blah, and it's important for the contact process. You're still going to look at the contact process this year. Okay. So sulfur dioxide reacts with oxygen and gives me sulfur trioxide, SO3. It's also called, no, it's not sulfate. Blah, 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 blah. At 8 minutes, it's here somewhere. Obviously, this little section there is 8 minutes. At 8 minutes, more oxygen was added to the container whilst maintaining a constant pressure and volume of container. With reference to the Chatelier's principle, fully explain the amount of sulfur dioxide was affected when the equilibrium was re-established. So, what we're doing, we are increasing the concentration of the sulfur dioxide. I'm just going to use a red pen. And then they want to know, using Le Chatelier's principle, explain how the amount of sulfur dioxide was affected when the equilibrium was re-established. So we're increasing the concentration, and how is that affected? So Le Chatelier's principle says what? If any disturbance is made to a chemical reaction that is in equilibrium, that reaction will what? Or you can just say a new equilibrium will be established that opposes your change or the change what you've made. In other words, we've increased the concentration of the sulfur dioxide. So now a new equilibrium will be established. There the equilibrium was. A new equilibrium will establish, and that new equilibrium will do what? It will oppose or counter the change that you've made. Okay. So how will the concentration of sulfur dioxide or the amount of sulfur dioxide was affected when the equilibrium was established? Why are they asking sulfur dioxide? Should I reread it? Oh, I'm lying. That's why I've got a problem. I just misread that data. Sorry. They've increased the concentration of the oxygen. That makes more sense. And they want to know, how will the concentration of the sulfur dioxide be influenced if we increase the oxygen concentration? Well, according to Le Chatelier's principle, if we increase the reaction, the concentration of one of the reactants, the reaction that opposes that increase in concentration will be favored. Okay, so what will happen? The oxygen that we increase, the concentration of oxygen that we have increased will be decreased. Do you agree? The change we've made will be counted. So the amount of oxygen we added will be counted. And the only way that will happen is this, if this sulfur dioxide reacts with the oxygen. So the concentration of that sulfur dioxide will decrease. Okay, fully how the amount of sulfur dioxide will decrease. Okay. Do you understand that?
Yes, I can. Yeah, I do.
Do you want me to repeat it?
No, I think I understand.
At 15 minutes, the temperature of the reaction mixture was suddenly decreased. Yes, you can see that because both rates drop. If both rates drop, then there's a decrease in temperature or pressure. Okay, but now the temperature is decreased. And this blue reaction, which is the reverse reaction, that one decreased more. You see that? While the forward reaction just decreased slightly. Right, now they probably want to know which one is in which one is exothermic. From the graph, determine and write down the reaction forward or reverse that was initially favored. Favored. According to me, there's no reaction that's favored if we decrease the temperature. Nothing is favored. Okay, let's figure it out. Is the forward or the reverse reaction endothermic? Well, if I decrease the temperature. If I decrease the temperature, this reaction falls radically. That means I'm taking away heat on this side. I'm taking it away by decreasing the temperature. If I take it away, that reaction will not decompose. So the forward reaction is what? Exothermic. We can test it. We can test it another way by saying if we decrease the temperature, the exothermic reaction will be favored. No, I'm wrong. Let's redo it. Tell me what mistake have I made. If you can, we can decrease the heat. Tell me if I was wrong or if I was right, and how can we test that? We know that the temperature was decreased. Both of them fell. But the one that falls the most is this blue one. The reduction in temperature favors, oh, this is right. So I wasn't wrong, I was right. So heat is given off here. If I remove the heat, then this reaction will not occur. It will drop in rate. And these two rates will go up. So initially, okay, I understand what they're saying, but they shouldn't say it like this. Write down the reaction that was initially favored, and that's the forward reaction. It was initially favored. But according to me, no reaction is actually favored. Is the forward reaction exo or endothermic? Exothermic. No explanation is needed. Okay, good. Right. Do you understand this one?
Yeah, it makes sense.
Good. Okay, this is the same sum. I just added another section to it. Okay, I'm not going to ask you to state Le Chatelier's principle. You have to go and study that. How will each of the following changes affect the yield of SO3 at equilibrium? So I'm going to change a couple of things. I want to know how the yield, you can think of this as the amount of mole. How will the amount of mole or the concentration of the SO3 be changed? Will it increase, decrease, or remain the same if I increase the pressure by decreasing the volume? So I'm going to decrease the volume, and that's going to affect that my reaction takes place at a higher pressure. Which reaction is favored if I increase the pressure? The reaction side that has the least amount of moles or produces the least amount of moles. So my forward reaction is favored when I increase the pressure. And this will allow for more SO3 to form. So increase. I'm going to increase the temperature. Right. I'm going to increase the temperature. Increase in temperature favors what? The endothermic reaction. Now, the forward reaction is exothermic. The reverse reaction will be endothermic. If the reverse reaction is favored, then this will increase in the amount of moles, and that one's moles will increase, but this one's moles will decrease. So the answer is decrease. Good.
Yes.
Last one, same question. After 5 minutes, the concentration of oxygen gas in a container was found to be 0.9 moles per cubic decimeters. Calculate the value of the Kc between 5 and 10 minutes. Also take into account that initially 5 moles of SO2 and 3 moles of oxygen was placed in a 2 cubic decimeter container. Right. So calculate the Kc between 5 and 10 minutes between this. So there we have equilibrium. We need to calculate the Kc value. So I want to make sure that this is probably, I'm just going to make that graph larger. This is probably 3 mole. Looks like it. The others we can't determine. Right, you're going to set up a table and try and get it. I'm giving you 4 minutes to make your own table. And then I'll do it. You can ask me just to give you a tip if you're struggling with something.
You're supposed to take the mole from the graph, right?
Um, yeah, well, yes and no. Initially, they're giving us the amount of SO3. These are your initial amounts, 5 and 3. Okay, so when I set up my table, let's just start there. Just going to set up this table because I haven't really thought of this. We're starting with SO2 and we're adding oxygen, and the product is SO3. So are we working with mole or yeah, mole? So initial change equilibrium, and then I can actually work out the concentrations after that if I want to, or on the same. So initially we started. Look, I'm not asking the Kc value there. I'm asking it after the first change. Do you understand that?
Mhm.
Okay. So we can use 5 mole as the initial SO2, and we can use 3 mole as the initial oxygen, and 0 of that. Now at equilibrium, I have, let's just see this oxygen. Where is this oxygen? Oh, there's the oxygen. At equilibrium, I'll have 3 moles of SO2. And at equilibrium, I don't know how many oxygen there is, but it doesn't matter. I have an equation, and the ratio is 2 to 1 to 2. You agree with that?
Yes.
So from this table, I can actually see that I've lost 2 moles of SO2. And therefore, I've gained 2 moles of SO3. Because they are in a 1-to-1 ratio. And I will only lose half of that oxygen. So it's -1 because the oxygen SO2 is in a ratio 2:1. So at equilibrium, I'll have 2 moles of oxygen, which doesn't look right. Do you agree? And
Mm,
I'll have 2 moles of SO3. That isn't correct.
yeah.
Not well, it's correct according to the calculations we're making, but the graph doesn't look like it. The oxygen looks like 2 moles. You agree? But the SO3 is more than 2. That is quite interesting. We've done nothing wrong. Everything is correct. Just want to look at that equation again. We've stuffed up the equation. No, we haven't. 2 to 1 to 2. So you agree that this definitely looks like 3 moles there.
Yeah, yeah.
And this would look
Definitely.
like 2 mole or 1.5.
Mhm.
And that I'm not sure. But those lines are supposed to be on top of one another. It's kind of wrong. The graph below shows the number of moles of each reactant. No, I don't agree with that. Okay. There's something we missed because we didn't read 6.3.1. Let's just make sure that everything is fine because they are telling us that after 5 minutes, which is there, the concentration of the oxygen in the container was found to be 0.9 moles per cubic decimeter. So the concentration or the mole is the concentration times the volume. And this is oxygen gas. Okay, the volume is 2 cubic decimeters. So the amount of mole is 0.9 times 2, and that is 1.8 mole. Okay, fair enough. So the oxygen there is 1.8 mole. 1.8. Right, so this is all wrong. That 3, I mean, this graph wasn't drawn very good, so we can't just assume that. Looked. So basically, what we've done here, if we had a proper graph, we would have probably seen that this isn't 3, but maybe just below 3. Do you agree? So we
Yeah.
were fooled by the small graph thinking it was 3. But the oxygen at equilibrium is 1.8. That means we have lost 1.2 mole. That means this one will lose 2.4 mole, bringing it just below 3, making it 2.6. Now, if the oxygen loses 1.2 mole, I will gain 2.4 moles SO3. So this one will be 2.4. Okay, now we can work out all the concentrations. It's quite easy. Okay, let's fill in these values. Mole, mole, mole per cubic decimeters. Okay, this one will be 0.9 apparently. And this concentration will be mole divided by volume. So that is 2.6 divided by 2 is 1.3. And this one, the concentration is the mole divided by the volume, 2.4 divided by 2, and that is 1.2. So these are my 3 concentrations. So now we can work out the Kc value. It's a nice example. The graph was just a little bit small to actually see that.
Why is it 0.9? Oh, okay, never mind.
No, they give that to us. So it's just 1.8 divided by 2. But they're giving that to us. So the Kc expression is what? Where's my equation? It's SO3 to the power of 2 divided by SO2 to the power of 2 times oxygen gas. So our Kc expression is 1.2 squared times 1 over 1,3 to the power of 2 times 0.9. Calculate that. Zero comma 0.95. So this is not a big yield. 7 marks. You see, we almost made a mistake. Let's explain where the mistake is. We almost made a mistake because the graph was so small on my screen. I was pretty sure that that was 3 moles, but it wasn't. It's just below 3 mole. So when these two values didn't end up to be the same, because they should be, then I realized there's something wrong. And then we saw this. I don't know, we read it, but we didn't incorporate that. The concentration is 0.9 mole per cubic decimeter at equilibrium, and that changed the values for us. Okay, let's just answer the other two questions. What disturbance occurred after 10 minutes? Remember, this is a mole time graph. We increased the concentration of oxygen, didn't we? We just added oxygen. And that means the SO2 will react with the oxygen. That's why that one goes down. And more SO3 will form. That's why that one goes up. Does this disturbance change the effect, change the Kc value? No. No change in Kc value. Because it's not a temperature change. Okay, there's 20 minutes left, Kutsa. Where do you want to actually start doing revision? On what?
I want to start doing revision on mechanics. I think that's the most important.
Newton.
Yeah.
Okay.
I actually want to do as much as I can when it comes to
Right. I have a box here. It's got a mass of M. I don't know the mass. There's a frictionless pulley system with a 3 kg block or ball attached to it. There's T for tension in the rope. Okay. Let's say that the system is moving to the right, or that block is moving to the right, it's accelerating at 0.5 meters per second squared. So that one is moving. And let's say that this kinetic coefficient of friction is 0.3. So there's a kinetic coefficient of friction was of 0.3. There's a 3 kg ball attached to a rope and on a block. And that block is moving to the right or accelerating to the right at 0.5 meters per square. First thing, I want to draw a free body of M. Quickly help me. Can you remember? Just fill in stuff that you can.
tension.
So I've got weight.
Tension.
Normal. Okay, tell me, do you use FG for weight or just W for weight? Weight.
In this case, W.
Okay, you can use W or you can also use FG if you want to. Doesn't matter. Same thing. FG is the force of gravitation and W is the weight. Then I have tension in the rope. And then I have friction. Is that correct? A free body of the 3 kg would look like this. Tension in the rope is upwards and weight is downwards. Is that correct?
Yes, okay. Wait,
Okay, so the question
yeah.
is, I'm going to break up the question and make it easy. The first part is No, I can't really break up the question. I want to know, this is just one big sum then. I want to know what is the mass? What is M's mass? What's the mass of M? Okay, method. The method is important. We're going to do a F net calculation of MA equals MA of M, and we're going to do a F net equals MA of the 3 kg block. And then we're going to substitute those two into one equation. I'm going to write in black. The red doesn't look nice. Eh? Is the red bothersome?
No, not really. I actually
But
can
the
see
black is
clearly.
better.
No, yeah, the black is definitely better.
Okay, good. So F net, I'm going to use the direction to the right down as positive. So F net is minus friction plus a positive tension in the rope, and that will equal M times 0,5 because the acceleration is 0,5, which means I need to get the friction, okay? But I don't know what to do, so I'm just going to leave this. I'm going to the other sum, and in this sum, the weight component will be positive, and the tension in the rope will be negative, and that will equal 3 times 0,5. So the weight minus the tension in the rope is 1,5. Is that correct? Okay, the weight we can determine actually. That's mg. Okay. So tension in the rope equals mg, which is 3 times 9,8 minus 1,5. You got that? That's 227,9 equals tension in the rope. That's my first equation. I was stuck with the left one, so I worked out the right one first. Now I've got tension and rope. So I'm going to substitute 1 in 2. So now I have negative friction plus 27,9 equals 0,5 big M. Is that correct?
Yes.
But I can get the friction in terms of M. The kinetic friction is the coefficient times N. And N equals W according to this diagram. So N equals mg. So the kinetic friction is 0,3 or 0,3 times mg. And that is 0,3 times big M, which is the mass, times 9,8. 9.8 times 0.3. That is 2,94 M. That's the friction. So now I'm going to substitute that. Therefore, minus 2,94 big M plus 27,9 is 0,5 M. 27,9 is 3,44 M. 27.9 divided by 3.44. 8,11 kilograms. Okay, so you haven't done something like this for a while. But this is a harder sum or a difficult one. Why? Because it just throws you off balance. Because normally you have to work out the acceleration and you get the mass. But now you didn't get the mass and you got the acceleration. True. Kuto,
Yeah.
can you hear me?
Yeah, I can.
Are you quiet today?
No, I'm actually what?
Are you processing it?
Yeah, I'm processing it.
Okay. Let's do another one. In this one, we have a 30-degree angle there, and there's a box, which is like 10 kg, but it is in rest at the moment. So the first question is, I want you to draw a free body diagram of all the forces on the 10 kg block. Okay, so we're going to start doing a normal that is perpendicular to the surface. Then there's a frictional force. How do I know there's a frictional force? If there weren't no friction, it would have just slided down and not been raised. And then I have a component here which is called the weight parallel. And I have a component here that's called weight perpendicular. I don't have to have those two components. I could have combined them into one that says weight. But that would make calculations harder. So I'm just doing that. Look at that. Quickly draw that.
Okay.
Are you back?
Okay. Yeah.
All right. Okay. So next question. What is the static friction force? Well, I can see these two forces are in equilibrium because the box not moving, then they are just the same. So I'm starting with saying that F net is 0. The net force is 0. Great. Therefore, the weight parallel plus the friction, not F is, long is, okay, I'm going to leave that as positive because the sum needs to give me an answer, is 0. Okay, so the friction force is negative the parallel component of the weight. Now, what is the parallel component of the weight? That one there is mg sine alpha. That you must learn. And the perpendicular component is mg cos alpha. So that is negative mg sine alpha. And that is negative, is it 10 kg? Yeah. 10 times 9,8 sin 30. And if you've been studying maths, you can do that without a calculator. Is that true?
Yeah, that's actually true.
Static friction is 49 newtons. Upslope. Okay, next one. What is the coefficient of static friction? This is the last thing we're going to do. I want you to take 2 minutes to try and figure it out.
Right.
All right, do you know what to do? If you don't know, let's just write the equation. Oh, K is wrong, it's static. Me S N. That's the formula, isn't it? Okay. So basically the formula is going to help me. I already have 49 there. And I only need n. Do you know how to determine the normal force? The normal force
Yes.
plus the weight perpendicular is 0. Or you can just say the normal force equals the weight perpendicular. So the normal force is mg cos alpha. Good.
Yes. Okay. $84,
Okay, let's do that. It's 10 times 9,8 cos 30. What's
got
that?
84,87. That's what I got. Yeah, 84,87.
Okay, what I'm going to do, I'm going to, for my purposes, I'm just going to leave it as 49 root 3, isn't it? Because that's not the question. Or you can write it as 84,87 blah, 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 no, Newton. As long as I take that whole answer in there. So I'm going to divide 49 with that whole answer and get the static coefficient of friction. So I'm just dividing 49 with answer and I get 0,58 or 0,577. Also very important, tan alpha equals mu s max. If there are no external forces. If no one's touching that thing, look, that block can be static. Do you agree? The block can be static, but someone is pushing it from the bottom or holding it up. Then the block is still at rest. Do you agree?
Someone's holding it up. Yes, okay.
Yes, okay. But now no one's touching that block. So there's no external forces on that block. Then I could have just done this. Tan 30 equals mu s. If you type in tan 30, then you get 0,58. Or 577. But if you don't understand it, you don't have to work with that. You can always get away by just using normal sums.
Can you? Okay. Something. Just something I want to see here. Okay.
You happy?
Yeah.
All right, I'll see you then next week, Sunday, I think.
Yes.
Kill the maths, do well.
Yeah, thank you.
And I'll see you next week. The lessons now, we're just going to do revision. And mostly we're going to do questions that you're asking. There's not enough time to run through all the work or teach through it or explain through it. Most of our work that we're going to do now are examples that you are sending me because it's something you're struggling with. Otherwise, I'm just going to waste your time by explaining things that you already understand. Have a nice day.
All right. Thank you.
Good to keep on.